I invite you to take a little quiz here about the properties of Hermitian eigenvalue problems. So pause the video and try to make up your mind about each of these 4 different statements. First question, are the eigenvalues of Hermitian eigenvalue problems real? Well, if you look in the textbook, there's indeed a whole proof where we show exactly that. So as soon as you have a Hermitian operator, its eigenvalues will be real. So that's a true statement. Moving on to the next question, there's also something in the textbook where we show that eigenvalues are positive for an eigenvalue problem. However, this is not for any arbitrary generic eigenvalue problem, which is Hermitian. This is true only for a very specific choice of operator, namely for the operator that corresponds to Maxwell's equations, to the Helmholtz equation. So this is not in general a true statement. Moving on to the third question, which is a bit tricky. What we actually write in the notes is that it's possible to construct a set of orthogonal eigenfunctions. We never say that any arbitrary eigenfunction that you find in the wild will be orthogonal to any other eigenfunction. And to illustrate why that's not true, let's take a look at when we have degenerate solutions. So say we have an operator, theta, and we find a certain eigensolution h1 with an eigenvalue lambda. And suppose we have degeneracy, which means we can find a different solution h2 with the same, exactly the same eigenvalue. So by accident, this sometimes can happen. And let's also assume that these two solutions that we find, h1 and h2, they are orthogonal. So far, so good. But now what we can do is we can, for example, take the first equation, multiply that by alpha, and take the second equation, multiply that by beta, and then sum them all up. Then we can write, because everything is linear, we can write then that theta alpha h1 beta h2 is equal to lambda alpha h1 beta h2. Now what we've written down here is nothing more and nothing less than saying that the quantity between square brackets here is again an eigenfunction of our operator with the same eigenvalue lambda. So we've constructed a new eigenfunction, and we can ask ourselves the question, is this eigenfunction orthogonal to, for example, h1, which we originally started our argument with? Now if you calculate that scalar product, obviously if you do h1 with h2, that's 0 because they're orthogonal, but there's also contribution from h1. So you clearly see that this new eigenfunction here, which is a bona fide eigenfunction, is not orthogonal to this h1. So therefore, in general, the only conclusion is that it's possible to construct a set of orthogonal eigenfunctions, not that all eigenfunctions will be orthogonal to each other. So that's a very important remark. The final question about a solution and then taking that solution multiplied by a constant. Now this is more like a semantic discussion, but if you have an eigenfunction and you multiply that by a number, this is still considered to be part of the same eigenfunction, the same equivalence class if you want. So h and alpha h are not considered to be degenerate separate eigenfunctions, but rather the same eigenfunction.